This is Physics 2211, Lab 2, about projectile motion. So an introduction to this lab is that the purpose is to compare position versus time graphs of experimental data of a projectile and a computational model, both with and without drag of a projectile. The models used are an experimental model using Tracker and a computational model using GlowScript, and the fundamental physics principles that are in this lab is just projectile motion, and then the result of this experiment was that the computational model more closely matched the experimental model once drag was considered. So the main physics idea of this lab was projectile motion, and projectile motion is a form of motion experienced by an object that moves along a curved path under the action of gravity only, and that is the equation for projectile motion that we will be concerned with for this lab. The procedure was that I first recorded a video throwing an eraser up from a set point. I imported the video into Tracker and cut the video to start after the eraser left the person in the video's hand, so that the only force acting on the eraser was gravity in the time period that the video played. I then tracked the motion of the eraser frame by frame at set time periods. I then created a computational model of the projectile in GlowScript by putting my information into the starter code that we were given, and then I created a spreadsheet and generated a graph comparing the experimental data with the computational data. And the system of this experiment was the eraser that was thrown, and the surroundings were everything else. So here's a screenshot from Tracker showing the experimental model. You can see the tracked motion of the eraser as well as the graphs on the side that Tracker produced from this video. And so here's the main information that we want from the experimental model, the initial conditions. And so there's a screenshot of the initial time, initial x position, and initial y position of the eraser. The total time of the video was 0.7 seconds. And then the initial x and y positions are seen there as well. So now onto the computational model. Here's a screenshot of the code. You can see this screenshot is from when with drag. So I put that with drag, it was 0.7, but without drag, the code was the same, just with 0 there instead. So you can see that information as well as the net force, velocity, and position were also considered, as well as the time. And so here's the results of the computational model without drag and with drag. So you can see the difference in the graphs and the diagrams adding drag. And my final drag that I ended up with was 0.7, as I said in the last slide. So now's a comparison of the Tracker data, the computational model with no drag, and the computational model with drag. As you can see, after adding drag to the computational model, it a lot more closely matched with the Tracker data than it did without drag, and it is a pretty good match, as you can see from the comparison. So now some possible errors that could have happened that resulted in the lines not being the exact same. One of these errors could be that I did not find the exact drag from the real-world experiment. I kind of just used a guess and check model until it looked similar, so there's probably a more accurate way to do that. There could also be some human error using Tracker. Sometimes it's hard to find the exact center of mass, so that could have affected some things. And then there could have been forces other than gravity and drag acting on the projectile, such as the fact that she did throw the object originally, so that could have put some force on the eraser as well. So now for the additional questions. For the what does it mean question, my answer to this was that the computational model with drag predicts terminal velocity, as the net force in this model would be 0, since it considers both the gravity and drag forces. And for the what if question, my answer was the time taken for the object to reach the ground when thrown upward is longer than when simply dropped. The object spends extra time moving upward before it even begins to fall, adding additional time compared to an object dropped from rest. If air resistance is considered, it would further increase the total time because drag would reduce both the ascent speed and the descent speed slightly. And that's all. Thank you.